Okay, so for particles, again, the probability distribution, again, is a function of x. The probability is a function of x um, of having a bullet hit the backstop at a particular position is proportional to, is equal to the sum of the two probability distributions corresponding to when one slit is closed and then the other is closed. Okay. So there, it's pretty simple. You get a very simple distribution, and you just sum probabilities. Okay. Now, what happens if we take a double slit experiment where we have waves? Let's think about water waves. Let's avoid light for the moment, because that's what we're trying to figure out: is what is light, what are photons, and let's just think about water waves. Well, if we do the same experiment with water waves, so imagine that in this position here in the at the source, we have some sort of plunker, some sort of thing which dips into the water in a periodic way so that it disturbs the surface of the water, creating these spherical waves that emanate from that position. These waves then hit the wall where there are two holes or two slits, and basically what happens is that these slits are the source of two new spherical waves, one for each slit, that again spread out from this point, and then what you do is that you have some detector again that you can slide over. You can slide up and down along this direction is still the x direction. Well, it's the positive x direction is this way, and so again you're basically doing the same kind of experiment, but now you're not counting particles. The detector now is basically measuring the height of the water wave. Okay, so it's measuring the amplitude of the wave, the height of the wave, and we know, well, at least you should remember from some previous courses and some previous work that the intensity of a wave, okay, is proportional to the square of the height, or the square of the amplitude. In this case, the amplitude, this is a water wave, so the amplitude is the height of the wave. Okay, and this intensity basically is a measurement of the rate at which energy is carried to the detector by the wave. Okay, and its intensity, so it's basically per unit area, but that's a detail. Okay, and for waves of this kind, water waves in particular, right, we can have the intensity can take on any value. So the wave height can be any value. It doesn't have to be. It doesn't have to come in discrete differences. And so you can have any height in your water wave. You can have any amplitude of this wave. So it's a continuously varying variable. It's a continuous variable. It doesn't have to take on discrete values. Okay, so it's not quantized. So this is the experiment, and now again, if we just open one of the slits at a time, then we get a distribution we get two distributions that look very much like what we saw with the particle. So again, if you block slit number 2, then you're going to get this intensity distribution I1. Again, this is a function of x. X again is along this. In this plot, x is the vertical direction to correspond to the actual physical experiment schematic, and to the right here, this is intensity, or in the previous case with bullets, that was just the probability. Okay, and so we see these two different distributions that correspond to one slit being closed, only one slit being open at a time. Okay, and but what we see now is that when both slits are open, we get something very different than we got before for bullets. Now we see interference. Okay, and we find that the intensity distribution when both slits are open, I12, is equal to the instead of being equal to the amplitude squared of or the probability, the sum of the probabilities of the two intensity distributions. Sorry, not probability, intensity distributions. It's actually, we first have to add the heights of the two waves, and then we square it. So basically, we're adding amplitudes first and then squaring. And if you work it out, then it looks like this.